Hello. You should hear me
Hey,
now and everything should seem okay. Is that, do you see the desktop and do you hear my voice?
yeah.
Okay, and I hear you.
Yes.
Good. Okay, great. All right. Okay. So I hope the exam went okay. I'm not sure when it'll be graded. There's 60 exams now to grade. So I hope that I can get them done in a week or so. It's going to take quite a while. It's not going to be an easy exam to grade. Okay, so it won't be graded probably for at least 1 or 2 weeks. I also gave an exam in another class last week, so I have 100 exams to grade right now. So this is going to take a week or so to get them done. Okay, so what we're going to do today is, well, first, you have this programming assignment due next week. Let's see, that's a week from today. So if you have questions about that, let me say first, has anybody had a question? Has anybody come up with any idea or anything that they want to ask about this assignment right now? Any question they'd like to ask right away?
Oh, um, I have a question.
Mm-hmm.
For the structure uh, processor data that you have us using,
Uh-huh.
you have an integer that holds the affinity mask.
Yes.
I'm a little confused at what number we actually put in for the affinity mask, if that makes sense.
Yeah. Let me pull it up.
Like, because I know it uses a hex number for the affinity command, but then we're representing it in binary. I'm just confused of what we use.
Well, any number, let's see. Okay, so let's see. Let me launch a CMD just for the heck of it. Okay, now let me open up Task Manager and look up that CMD. Okay, and details. Okay, there's that CMD I just opened up. Okay, notice, remember, affinity in my computer, it's 12 bits. There's 12 bits of infinity from 0 to 2. Okay, right? Now, suppose this processor had CPU 4. Suppose that, suppose this process, its affinity was CPU 4. Okay, 4, if you write that in binary, that's 1, 0, that's 1, 0, 0, 0, 0. Okay, so that's 1, 0, 0, 0, 0. Okay, so what number is that? Okay, now you can't write binary in C. C doesn't allow binary. So you would write that in either decimal or hexadecimal. In hexadecimal, that'd be 0x10, because these 4 bits are 0, and then the next 4 bits have a 1 and then all zeros in front, right? And if you wrote that in decimal, what is that number? 2's place, 4's place, 8's place, 16's place, 32, right? So now in that data structure, you have to where is it? Oh, here, int, affinity mask. So what number would you store in that int?
32.
Or 0x10. You can use, those are the same number. You can write it in hex in C 0x10, or you can write it in C as 32.
Okay.
Yep. And
that makes
now,
sense.
pardon
me? I just said that made sense.
Yeah. Now,
That's
affinity masks in this case are always 1 bit. Now, that's the affinity mask you put in here. Now, let me go back and do another example. This CMD might have the affinity mask like that. Okay. Now, the parent process, the process that you're writing, can have an affinity mask like that. But when its children processes always have an affinity mask of just a single bit. Okay, so in this data structure, this is always just says just one bit set. Okay, but when you get the processor affinity mask for this process, it can have multiple bits set in it, and you have to find them. Okay, so you have to find out what are the bits that are set in the affinity mask you're given. So you're given, that's like this process here would have that affinity mask, and then your program would be running under the affinity mask of whatever CMD was run in. So this program gets its affinity mask, okay, and that affinity mask can have an arbitrary number of bits set, okay. But then when it sets the affinity mask, when it creates and then initializes the processor pool, well, we're trying to remember where it would be in here. But it's not really in this outline. It's described in the web page. You know, when you get from the processor pool a handle, you have to find out what CPU that process is running on, and that's where you use you get this strut out of the processor pool, and then you look up in it what CPU it's running on, and that's the CPU that you would launch a new process on. So if the process that ran on that CPU terminates, then you'd run a new process on the CPU. So in here, when you get from the processor pool handles to the currently running process, well, that handle also tells you then once you have a handle to this, then you could figure out what its affinity mask is, and then you'll launch the next process with the same affinity mask. Okay. Okay. So yeah. Okay. So these numbers actually, so another way, these numbers are always either 1, 2, 4, 8, 16, 32, or 64. Yeah. See, they're single, there's just one bit set. So they're the only numbers they can be are 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 100, 1024. Yeah, that would be up to, I forget how many bits I did there. Okay. So they're the powers of 2. So that's what goes in here. Okay. And when you get the processor's affinity from the operating system, that's the process that this thing is running under. It could have arbitrary bits set, and you have to pull it apart. You have to write a little loop that steps through these bits and checks which ones are set. Yeah, you have to write a little loop that steps through all the bits in this word and sees, and you do that with bit shifting. You check if this bit's a 0 or 1. And then after you check this bit, you shift all the bits to the right, and then you check this bit again. Then you shift all the bits to the right, and you check this bit again. Then you shift all the bits to the right, and you check this bit again. That's one way to do it. I mean, you could actually, that's one way to do it. Another way to do it is you can actually just check that bit, check that bit, check that bit, check that bit, check that bit. Different people have written, there's a whole bunch of ways of checking and if you Google it, you'll find lots of different descriptions of how to find the bits in a word. Yeah. How do you figure out if you have an int? How do you compute which bits are 1 in the int? Okay, so it's not a hard thing to write, and it involves some bit shifting. Yeah, it involves what people refer to as bit manipulation. Okay. All right. So so the processor affinity mask you get from the operating system can be any number, and you have to figure out what bits are in it. And the process affinity mask you write into here is always, it's either going to be 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. It's one of the powers of 2. Okay. So now what about another question from this stuff here? Any other question about the homework assignment? It's not an easy assignment. You will not write it in one evening. I mean, I couldn't write it in one evening. Okay. Yeah. You will not write this in one evening. You should get started on it as soon as possible. Yeah. And like I say, it has to be done in steps. You really have to you have to think through how you're going to get it done in baby steps so that you can have something to fall back on when it blows up. You can go back and say, well, this much was working. So, what did I change and now it's not working? You cannot write it and then debug it. There's two things that are impossible: to write this thing in one day or 2 days, and another thing that's impossible is to write this thing and then debug it. You have to build it up in steps, like any real software. The assignment like this is an assignment like real software. You're ready to start learning how to write real software. You know, where you have to, it's too complex to just write it in one pass and then debug it. Okay? You really should think through what would be a unit of this that I could write and debug. Then what would be an additional unit I could write and debug? And then what would be an additional unit that I can write and debug until it's all written and debugged. Okay. Any last question? Any other question about this? Okay. Well, what we're going to do today is probably finish talking about the multi-level feedback queue. Okay. So I'm not sure if we'll finish it or not. Okay. Talking about the multi-level feedback queue. And then the next chapter in the book is to start talking about virtual memory. So I haven't put the reading assignment up there. I probably, maybe I'll just wait till Wednesday to put it up there. But we're not going to do the lottery scheduling or multi-CPU scheduling. Okay. It's be better to just go ahead and start the next section of the book on address space and virtual memory. Okay. So this is the multi-level feedback queue is the scheduler in Windows. It's not the scheduler in Linux, but it's a scheduler in Windows, and it's a very popular kind of scheduler. So it's a good one to learn. I don't even know if the lottery schedule. I've never quite understood why he does this lottery scheduling. It's a little bit complicated, and it's not what Linux uses either. It's not what Windows uses either. I'm not sure why. I'm not sure who uses the lottery scheduler. Okay, so if multi CPU scheduling is important, but it's just too. Yeah, it's just it's more important to do virtual memory. It's more important to do virtual memory than to do the multi CPU scheduling. Okay, all right. So now here's the motive. Let me do something to show you the motivation for the multi-level feedback queue. Now, what we've been doing. Let me download the folder on scheduling. The notes are in this folder. Okay. Now, we've been going through these algorithms, okay, and we've seen what they're kind of good for. Uh, uh, Shortest job first and shortest time to completion first gave you good response time, okay, and round robin. I'm sorry, shortest job first and shortest time to completion first give you good turnaround time, and round robin gives you good response time. Okay, those are our two important metrics: turnaround time and response time. These other metrics, we're not really spending much time thinking. The book mentions them, but these two are the ones that dominate the thinking: turnaround time and response time. Okay, so the algorithms we're working on, those are the two metrics that are the most important. We want good turnaround time and good response time. And all these are important metrics too, but the algorithms we're looking at don't really necessarily, in the broad scheme of scheduling, all these metrics are important, but from our point of view right now, these are the two metrics that we were dealing with. Okay, shortest job first and shortest time to completion first give you good turnaround time. Round robin gives you good response time, and they kind of both do poor in the other. Like where turnaround time gives you good, where shortest time to completion first gives you good turnaround time, it gives you very poor response time. Okay, and round robin, where it gives you very good response time, actually gives you very poor turnaround time. So it's like they're really opposites of each other. Okay, these are the two most important metrics, and they're almost like opposite of each other. To make this one good, you have to, at least with these algorithms, if you make this good, you make this one bad, and if you make this one good, you make this one bad. Okay, now the multi-level feedback queue actually resolves this. It actually comes up with a way of making more or less both of these good. By coming up with a clever algorithm, we ended up like, we're going to end up essentially blending these algorithms in a clever way so that we get reasonably good turnaround time and good response time. Okay, so the multi-level feedback queue is a blending of algorithms that gives you good thing both for turnaround and response time. Okay, and it will also it puts priority in there. So one of the things it blends it blends round robin, shortest time to completion first, and priority. Okay, so these three things will get blended into the multi-level feedback queue, and then you get good turnaround, reasonably good turnaround time, and really good response time. Okay, now shortest time to completion first is essentially, remember, a fancy version of shortest job first. Okay, and yeah, so what we're going to do is essentially these three things get blended into one algorithm. Okay, now here's in this folder, there's another note here that gives you a sense of what it is we're trying to do. So let me open this one. Okay, this is an example. It's an example of one with a timeline. So like in the textbook, we use these timelines for really figuring out what we're doing. So you know, um, these kinds of timeline, he draws them like this. I'm drawing them like this. It's just a one dimensional. He kind of draws them looking like bar charts, which I'm not really sure why. Remember, the only thing that's really important here is the interval at the base. The height, these aren't bar charts, they're just intervals on the number line. Okay. So here I just draw them as intervals on a number line. In this interval, I'm running process P1. In this interval, I'm running process P2. In this interval, I'm running process P3. The tick marks represent when you change from one process to another. Okay. The length of these tick marks are the time slice. That's the amount of time that we're using to give each process. So we're using this is essentially round robin. This algorithm here is essentially a round robin scheduling. Okay. Okay, which gives us good response time, but not good turnaround time. Okay, so we want to see something about round robin. Okay. Now, in this round robin system, what I have is it explains up here. I have 5 CPUs, I have 5 processes, 1 CPU, 5 processes, 4 CPU bound, and 1 IO bound. Okay, so 4 CPU bound processes and 1 IO bound process and 1 CPU. Okay, all these examples, we just assume that there's 1 CPU for now. Okay. Now, if it was round robin, and process 0 is the IO bound one. So process 0 is the IO bound. Now, what that means is, think of a process that would be copying one large file from one hard drive to another hard drive. So suppose it's got to copy like a 10 gigabyte file from one place to another place. So all it's going to do is it would fill a buffer with data and then ask that buffer to be it would create a buffer and then ask for data from one file to be copied to that buffer. That would be an IO operation. As soon as the IO operation is complete, it would then write that buffer to the other file. Then when that IO operation is complete, it would ask for that buffer to be filled again from the first file. Then when that buffer got filled, it would immediately ask for that buffer to be written again to the other file. So the program actually literally does nothing but call a read operation to fill a buffer, then a write operation to write the buffer. So it reads from file A, writes to file B, reads from my file A, writes to file B. So it does no calculations at all. When you say it's IO bound, it really means that as soon as it gets to CPU, it's just going to issue an immediate, when it gets to CPU, it's either going to issue the read or the write. So it reads from file A, then writes to file B. Reading from file A will block while it takes a long time to fill the buffer with data from file A. Then as soon as that's undone, when the process is unblocked because that's done, it immediately just writes that buffer to file B. Okay, so that's an extreme case of, and that's a real common case of a process copying data from one place on a drive to another. So that's what we mean by IO bound. It really does nothing but it makes system call after system call after system call with no calculation. Okay, so here's how, if we look on a timeline, process P0 runs first in the round robin, but it runs for essentially 0 time because it just immediately makes a system call. Okay, so P0 runs and it makes a system call, and then it blocks, and then P0 gets the rest of its time. P1 gets the rest of its time slice. Then its time slice is over. P2 gets a time slice. Now, I'm assuming here that the IO operation takes 2 time slices to do. So this is how long it would take an IO operation, which is not unreasonable. Whatever your time slice here is, the time slices are pretty comparable to the amount of time it takes to do an IO operation. So an IO operation might be 1 or 2 time slices. I'm assuming 2 time slices. That means the IO operation is done here. So P0 is ready, but in round robin, you do P3, then P4, then P0. Notice from here to here, P0 just waited for its chance. Then as soon as it gets on the CPU, it immediately does, like this one did the read, then this one does the write. Okay, then process 1 gets the rest of its time slice, then process 2, here's where the IO is completed, but it has to wait. P0 waits until complete round, until you go all the way around the round robin, then P0 is here. Okay, then P0 immediately makes an IO request. You go all the way around the round robin, and then P0 is here, but its IO is done here. Okay, so what happens is, in a sense, P0 only gets to make half of the IO operations it could possibly do. Okay, so like it could have done an IO operation right there. Yeah. And the idea is if you broke the round robin and if you let P0 sneak ahead in line here. So the round robin was P0, P1, P2, P3, P4, P0, P. If you let P0 sneak in the round robin, nobody would actually care because P0 would take up no time. He's essentially a very short job. You know, it's like letting somebody buy a stick of gum in the middle of your checkout. It's not really going to cause you to wait any longer. If we now here's what it looks like if you let P0 sneak ahead. If you let P0 sneak into the ahead in line in the round robin, P0 can make an IO request here. P3 doesn't even notice it. Then P4. Now P0 is ready here. Yeah, as soon as his IO is done, you can let him sneak in. Okay, so the round robin is really between P1, P2, P3, P4, P1, P2, P3, P4, and P0 is allowed to sneak in whenever he wants to. Now the big question is, how can you get this algorithm? How would you modify round robin so that you knew that's okay for P0 to sneak ahead? Okay. Round robin just knows that there's a list of processes, P0, P1, P2, P3, P4. So it just goes through the processes, P0, P1, P2, P3, P4, P0, P1. It doesn't know anything about them. For the algorithm to do this, the algorithm has to have some sense that there's a good reason to let P0 sneak ahead. Okay. Now, but why P0? Why not P3? Why not let P3 run twice in a row? Right? What mechanism would we give round robin to let it know that P0 is okay to sneak ahead? Now, what essentially we know is that P0 is a very short job. See, when we let P0 sneak ahead, it just immediately makes an IO operation. Okay. So it immediately makes an IO operation, and so it doesn't really take up any time. And then you can let P3 finish, and then let P4 do its time slice, then let P0 sneak in. Its IO is done, let it sneak in, okay? Then do the round robin, okay? Okay, so the question becomes, this scheduling is way better than this one because P1, P2, P3, and P4 don't even notice that they've been interrupted. And the P0 makes twice as many IO operations. Notice that it's essentially getting better turnaround time for P0. P1, 2, 3, and 4, they're really not affected. And essentially, this is acting like shortest job first. This is the intuition that P0 is a short job. You let him sneak ahead in front of the others. And by letting him sneak ahead in front of the others, shortest job first gives you good turnaround time for the short job. He will get twice as many IO operations in there. And if his IO would be complete in one time slice, where he would be ready here, he would get even more IO operations done. And P1, P2, P3, P4 wouldn't really feel it. Okay, letting short jobs sneak in line in round robin is not going to hurt the other people in the round robin. So if the IO operation was done here, if you even made it one more level, yeah, if the IO operation was done here instead of, yeah, you could let P0 sneak ahead even one more time. You could let P0 sneak there. Okay, and in that case, P0 could do, way more IO operations. But P2 doesn't really know. Letting P0 sneak in there really doesn't hurt P2. Okay. Because the key is that P0 is a very short operation. Just does an IO op request and it's done. So it's on the CPU for probably just a few microseconds, and that hardly affects P2's time slice. Okay. So we need a mechanism that lets, well, what it amounts to is an IO bound process sneak ahead of other processes in the round robin. And this is what multi-level feedback queue figures out. Multi-level feedback queue is a way to let the short little IO things sneak into the round robin ahead of the things that are CPU bound. Okay. The things that are CPU bound that are taking a while to do, you kind of let these IO bound processes sneak in there. Okay. Okay. So now the question is, how do we do this? How do we make this into an algorithm? The intuition is here. Okay. Let IO bound processes sneak ahead of CPU bound processes in the round robin. But the question is, how do we manage to do that? Okay. Now, let me draw a picture to explain what we're going to do. Okay. I want the picture of the CPU states. Okay, this is a real important picture. We're going to use this picture here. One way to think about this picture is that there's only one process running. Okay, blocked is a bunch of processes, and ready is essentially like that's where the round robin queue is. Ready is a queue of processes, and you pick who's ever at the front of the queue to be put on running. Okay, and then if you are descheduled, you go to the end of the queue. Okay, so round robin is happening on these. This is essentially a round robin line where now if you are blocked, you go down here. And then here, this is not a queue. This is just a pool of blocked processes. They move from here to here when they unblock, and there's no ordering to them. The processes down here are just waiting. And at some point, one of them will be unblocked and he'll go up here. But when he goes up here, he goes to the end of the queue. So this one is a queue. This is just one process. This is just a bunch of processes, but this one is a queue, a line of processes. And when you unblock, you go to the end of the line here. And when you're descheduled, you go to the end of the line here. And whoever's ever at the front of the line is the one who gets scheduled. Okay, so this is where the round robin takes place. Okay. Now what we're going to do is take that picture and kind of modify it, make it a little bit more elaborate. Let's see if I can draw a good example. So I've got the ready part and the block part. And then what I want to do here is draw this one real big. So this is going to be running, ready, and blocked. But I want to draw this one real big. So then the arrows, see, I can put, oh, okay, yeah, remember, I just fill them in. Okay. This one is, you know, you're chosen here. This one is descheduled. Okay. This one's blocked. And this one is unblocked. Okay. Now, so running, whoops. One process is running. So this is just one process here. This is a bunch of processes that are blocked. Okay. Okay. Now, what I'm going to do here is this is going to be a bunch of queues now. Instead of it being one ready queue, this is going to be a bunch of ready queues. So this is the ready state. But what I'm going to do is I'm going to think of it as a bunch of queues. So there's going to be one, I'm going to draw, like, I don't know, a certain number of queues here. Okay. So this is a bunch of queues. Okay. And these are essentially priority queues. So we'll make this priority 0. That's the highest priority. Make this one priority 1. Then make this one priority 2. This one priority 3. And this one priority 4. Okay. And these are queues. So if I want, I can draw, you know, you wait in line. So there'll be a process waiting in line here and another process waiting in here. So this is a queue that holds multiple processes. Okay. So each one of these is a queue holding multiple processes. Okay. And we have to talk about how you move through these queues. What is the algorithm? What is the multi-level in multi-level feedback queue is these queues. These are the multiple levels. Okay. So multi-level feedback queue, feedback scheduler, these are the multiple levels. Okay. Okay. Now, let me erase this for a minute. When you unblock, you actually will go into the top level queue. Okay, so processes that unblock go to that queue. Okay, then the operating system does round robin on here. So there might be some process, I'll call it P, like there's some process P4 in this one, and there's a process P3 in this one, and process P7 is here. So this is some queue of processes. Okay. Okay. Okay, so the operating system is doing round robin on here. When the running process is either finished or gets blocked, and you pull this guy out and put him in here. So P4 would be the next process to run. Okay, so this is round. We do round robin on this queue. We're doing round robin on this queue. Okay, now here's where things get interesting. If a process goes this way, so this arrow here is you used up your time slice. As opposed to doing an IO operation and blocking. Okay, so used up a time slice as opposed to going this way, which was say an IO request. Or some wait. So you either made an IO request or a wait, but you blocked for some reason, okay? And then this one would be IO complete or waiting. Your wait is complete. What you're waiting for is complete. So you go from here to here, okay? When you use up your time slice, you go, this is a little bit tricky. Where do you go when you use up your time slice? Okay. You go to the next lower level than where you came from. Okay. So you would go it's a little bit, this arrow here, where do you go to? I'll just draw it as you go here. Oops. You go, and I'll annotate it as one level down. You go one level down. Okay. So if you came from here and you ran here and you finished your time slice, you'd go to 1. Okay. If you came from 1 and you went over here and you finished your time slice, you'd go to 2. If you came from 2 and you went over here and you finished your time slice, you'd go to 3. So you go to one level down, unless you hit bottom level. Then if you came from here and you went running and then you used up your time slice, you go back to here. But if you block, you go to the top level. Okay, so if a process used up its time slice, it has to move down a level. And if a process if it doesn't block, it moves down a level. If it blocks, when it unblocks, it goes to the top level. Okay, each one of these queues is a round robin queue. So this is round robin, but only after, what's the right way? You only do round robin down here after this one is empty, after above is empty. Okay. So each one of these queues has this property. So like this one here, this one is round robin, but only after the above one is empty. Okay. Then this one here would be round robin after the above one is empty. Okay. And same down this one. So they all have this property. They're round robin queues, but you only do them if the above one is empty. Okay, here's what that means. Take this process P4. You put him up here. Okay. If he blocks, he's down here. Okay, so he's probably going to block for a little while. Then you pull P3 out of here. You put him up here. If he blocks on an IO operation, he goes down here. So he's stuck down here. Then you do P7. Suppose P7 runs all the way through its time slice. He goes down here. Then you do P1. Suppose P1 runs and finishes his time slice. Then he goes down here. Now this queue is empty. Notice that this queue would probably would empty out because every process is either going to block and go down here and probably be stuck here for a while, or it's going to finish its time slice and then it moves down here. Okay, so this queue will actually probably empty out pretty quickly. Now, when this queue empties out, everything in it is either blocked over here or in this level down here. Okay, so now you would start running the processes in this queue. So maybe now this one is, suppose this one's emptied. So suppose there's some processes down here, like a P, I'll just write like some other numbers, P9. Once this one empties out, you start doing round robin on these. But pretty much the same thing happens. When this one is chose to run, it's put on here. If it blocks, it goes down here and it's just going to sit here for a while until whatever it's blocking for is ready. If it finishes this time slice, it actually doesn't return here, it returns down here. So then you'd go to this one. And if this one, you put this one on the CPU, it's either going to go down here and get stuck down here for a little while, or it's going to finish up its time slice, but then it goes down here. So you'll finish up these jobs. Okay. Okay. At some point, this is probably going to empty out pretty quickly too, however many processes are in here, because every process, notice that processes don't go from here back to here. They don't go from, none of these queues have this is the only queue where a process can leave that queue and go back to it. If a process leaves that queue, it goes either to here or to the one below. For all these queues, when a process goes to running, it either gets blocked, in which case it'll eventually go up to the top one, or it goes, if it finishes its time slice, it goes to the next level down. So when a process goes running, it never goes back to its level. It always goes to either blocked or a level higher. Okay. Now, so this is the algorithm. This is this is actually the whole algorithm right here. You got the ready queue is now a whole bunch of queues. There a whole bunch of what we call priority queues. Okay, priority 1 queue gets emptied out first, then you empty out the priority 0 queue gets emptied out first, then the priority 1 queue, then the priority 2 queue, priority 3 queue, priority 4 queue. Okay, the way the algorithm for emptying a queue out is that you pull the first process out, make it running. If it blocks, well, then it blocks down here for however long it takes. When it unblocks, it goes back up to this queue here. Okay. If it finishes its time slice, it goes down one level. And then that's the same true for all the other queues. When you pull somebody out the front of the queue and make them running, if he finishes his time slice, he goes to the next level down. If he doesn't finish his time slice and he blocks, then he just sits here and waits till his IO is completed, and then he'll go up here. Essentially, this is the queue of processes that are doing IO. This queue ends up being the IO bound queue, because if you're IO bound, you'll always block, then go back up here. Then you run and you will not finish your time slice, you'll block. See, that was this picture here, that an IO bound process doesn't take up a time slice. It's given the CPU, makes an IO request, and then somebody else gets to finish the time slice. An IO bound process does not use up its time slice. So that becomes our definition of IO bound. Our definition of IO bound is you did not finish your time slice. You were given the CPU, you're running, and you block before your time slice is over. So you are now labeled as IO bound. That means you get to go up here. And if you make another IO request immediately, you stay IO bound. You make your IO request, you wait till your IO is ready, then you go up here. And these processes, they're at the head of the queue, they're at their highest priority, so they get served really fast. Yeah. And essentially, the assumption is that if you've made a couple IO requests, you're probably going to keep making IO requests, just like this one. Make an IO request, make an IO request. See, when processes are IO bound, they tend to stay IO bound for quite a while. So all these processes would probably be IO bound, and they won't linger up here. They're not just going to keep, because what they do is they go running, blocked, then they sit down here for quite a while they wait for the IO to complete. The IO is going to take, the whole intuition here is the IO is going to take quite a while to complete. So you sit down here, then you come back up here and you make another IO request right away. These then are the jobs that are not doing IO. Actually, all of these would be jobs that are not doing IO. Now, there's an interesting thing about why you need a bunch of these. Why don't you just have 2 queues? Okay. Let me put a little number over here. Here is the amount of time quantum. Here's the time quantum for each queue. Suppose that queue has a 30 millisecond time quantum. And this one will have then a 50 millisecond time quantum. And give this one, say, a 70 millisecond time quantum. And give this one a 90 millisecond. And give this one, make it 150 milliseconds. Oops. Okay, the number I'm putting over here is the amount of time a process, the amount of time a process in that queue gets to run. Okay, so if you're here and you get put on the CPU, you run for 70 milliseconds. And then if you use up your time slice, you go down here. Then if you go back, then when you finally get your turn over here, you'd get 90 milliseconds. And if you use up your time slice, you go down here. Now when you get the CPU, you get a long turn on the CPU. Okay. What's the intuition for making these queues? Yeah, this here, you're given a short period of time to do your IO operation. If you don't do your IO operation in a short period of time, you assume you're no longer IO bound. So if you don't do an IO operation pretty quickly, you get put down here. The assumption that you're not quite IO bound yet, and you're given here you're given a little bit more time to run. Think about, suppose I have let's do a timeline, but without any IO operation. Suppose I have a timeline where there is no IO. So there's no process 0. There's just process P0, P1, P2, P3. There's no IO process. You want to think a little bit about what this picture means. What's going on here? There's just processes. There's 4 processes, P1, P2, P3, and P4 are all CPU bound. They don't do any IO. Okay. In that case, this picture is kind of dumb. Should I get rid of all the IO operations? Okay. P1, P2, P3, P4, P1, P2, P3, P4, P1. So round robin on the CPU bound processes, okay, is not really a good idea. Why? What's kind of, yeah, so they're CPU bound. They don't do any IO operation. But I'm going to go P1, P2, P3, P4, P1, P2, P3, P4, P1, P2, P3, P4. Okay. Now remember, the whole point of round robin is good response time, but has bad turnaround time. Okay. What might be a better way to do this? What's wrong? What's kind of not such a great thing here? Does anybody have a sense? Why would I say that it's, if they're CPU bound, it's really not a great idea to do round robin? What's not really good up here?
They don't finish very quickly
Why not?
because they have to wait for all the other processes to be done multiple times.
Yeah, so what would be a little bit better here maybe? There's 2 things wrong with this. One is exactly what you mentioned. Everybody takes a long time to finish. So what would be one process? What, notice that 1, 2, 3, 1, 2, 3. You notice how everybody's getting 3 time slices. What would be better maybe?
Increase the time they ran, so they only needed 2.
Okay, now that's one possibility. Now, how could I increase the round? Yeah, so what would that be? That would be Well, let's make the time slice 3 times bigger, for example. Then what would I do? Run P1, then run P2, then P3, okay? What about that? If I did this right, everything would still line up. Let's see, 1, 2, 3 time slices, 1, 2, 3, 1, 2, 3. Yeah, there. Is that better? So I made the time slices longer. So the time slice is now P1 gets to run, then P2, then P3, then P4. And suppose that that's all they needed. Suppose that they're completed at this point. Is this better? What's better about it?
P1, P2, and P3 finish a lot earlier.
Yeah, so P1, P2, and P3 are happy. P4 doesn't care. He's finishing at the same time anyway. See, notice he finishes at the same time anyway, but now P1, P2, and P3 are a lot happier. Okay, so since they were CPU bound, round robining on them really didn't really. Now, there is a sense that P2 got the satisfaction of getting on the CPU a little bit sooner than he did here. But it probably doesn't matter to him because he's probably more interested in when he finishes than when he got on the CPU. See, from his point of view of P1, P2, P3, P4, you might say that turnaround time, they're CPU bound for CPU bound processes. Turnaround time is probably more important than response time. Okay. If you're CPU bound, you probably care more about when you're done than when you actually got started. Like, okay, P1 got started pretty soon, P2 got started pretty soon, P3 got started pretty soon, P4 got started pretty soon. But then none of them finished till, P1 didn't finish till here, P2 didn't finish till here, P3 didn't finish till here, P4 didn't finish till here. For them, they probably care more about when they're done than when they got started. So if you've just got a bunch of work to do, if you're CPU bound, you probably care more about your turnaround time. You probably care more about your turnaround time than you care about your response time. Okay. Round robin gave you good turnaround time, but gave you real lousy response time. If you increase the time slices, essentially, if the time slice is long enough, he can do all his work in that time slice. He can do all his work in that time slice, and he can do all his work in that time slice. Okay. So if you make the time slice long enough, okay. Now there's another advantage of this one over this one. Okay. One advantage is by having a long time slice. Now remember, the long time slice is what's happening when you go down here. The time slice in this queue is way longer than the time slice up here. So as these processes move down, they look more and more like this would be what you look this is what you'd expect in a high priority queue. Okay, that would be the picture up here in a higher priority queue, and this would be the picture in a lower priority queue. Okay, so the lower priority queue has these longer time slices. The lower priority queue has these longer time slices, which kind of like make, if a process can be finished in that time slice, the next one can finish in that time slice, next one can finish that time slice. They feel like they're getting done faster than round robining. Now, what else is kind of bad about this one? See if somebody else can come up with something else. What happens at that tick mark?
A context switch.
Context switch, which is time consuming. We talked about that means you have to switch from user mode to kernel mode. You have to copy all the registers from process 1 into a data structure, then copy all the registers from process 2 into a data structure, and then relaunch process 2. So this is a context switch. So I could put that into the picture. What's true there is that this is a context switch. Context switches take a lot of time. Okay, but that means I have a context switch there. So in fact, this time here is actually longer than this one, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's like a dozen context switches here, and there's only 1, 2, 3 context switches here. So in fact, this one is actually going to be a tiny bit faster because I'm saving context switches. So in a sense, this one's actually going to be faster than that one. Okay, which is a subtle issue, that because there's so much fewer context switches down here, this one will actually be a tiny bit faster than this one were, because this one had to do context switch, context switch, context switch, context switch, context switch, and all those context switches were actually wasting of time. You're just switching between P1 to P2, then P2 to P3, P3 to P4, P4 to P1, P1 to P2, but you're just going to go back to them anyway. P1 is going to go back to P1, is going to go back to P1. Why not just let P1 try to do as much work as it can without being interrupted? Then let P2 do as much work as it can without being interrupted. That's why you want these long time slices down here. If processes move to this level here, they are really solidly CPU-bound processes. They're like these processes here. And there's really no good reason to switch from P1 to P2, or essentially, you see that as you switch from P1 to P2 here, and then from P2 to P4, all you're doing is wasting time on the time slice, on the context switch. You're not going to make things faster by context switching. In fact, you make things slower by context switching. If the processes are truly CPU bound, round robining on them wastes time on context switches. You're better off just running one process, then run the other, then run the other, then run the other, with a minimum of context switches. So that's what this algorithm is trying to do. It's trying to say that, hey, by the time a process gets to this level, we know it's really CPU bound. It hasn't made an IO operation request in a long time. It's probably not going to make an IO operation request for a long time. So let's just let it sit on the CPU for a long time. Now, as long as there's nobody in one of these higher levels, that means there's no short running job that wants to interrupt one of these. We just stick with these things in real long running time quantums. But if somebody unblocks, so suppose empty, and you're round robining down here. So you're making real efficient use of the CPU. Give this guy a real long time slice, then give this guy a real long time slice, then give this one a real long time slice. But some IO process unblocks. He immediately goes up here. Okay. As soon as he unblocks, he takes priority. He gets put on the CPU right away, but then he does another IO operation. And you're back down to here, because this would be empty, and you go back to round robining on these guys without much time slicing. Okay. On the other hand, so this is actually very efficient. It lets these short jobs jump ahead. Remember, we said our question was, how can we let P0 jump ahead in line in front of P1, P2, P3, and P4? And the answer is this algorithm here. When P0 unblocks, he goes up here. So P0 will go up here, and P1, P2, P3, and P4 are probably down here. Okay, so P1, P2, P3, and P4 are probably down here because they're CPU bound processes. And P0, every time he makes an IO request, he gets blocked, but then he unblocks up to here, which means that P0 would immediately cut ahead of these guys. He'd get to make his next IO request right away. He'd make his IO request right away and just get blocked back down here. Okay, so we would have the mechanism that makes P0 constantly get blocked, but then get a higher priority, then get blocked, but then get a higher priority. Whereas the long-running jobs here, they'll end up down here with very long time slices. Now, that's not shown here, but they'll end up with what this stock picture shows. They will end up with their nice long time slices so that you don't waste time switching between them needlessly. Okay. So now this is called multi-level feedback queue because there's multiple levels of queue, and the feedback is the way that algorithm says the way you leave running tells the algorithm where to put you. That's the feedback. When you block, the algorithm says, okay, now you go up to here. So that gave the algorithm information about you. If you blocked and you unblocked, didn't matter where queue you came from. If you make an IO request, when you finish with your IO request, you go up here to the top level. Because if you make one IO request, we're going to assume you're probably going to make another one real soon. If you don't make another one real soon, well, then you'll drift farther back down here. But if you make an IO request, you go to the top of the top queue. Okay. On the other hand, if you finish out your time slice, that's feedback. See, the scheduler notices that you used up a time slice, and it lowers you down one level to a longer running queue. And then if you still finish your time slice, you move down to even a longer running queue until you get down here to the really CPU bound processes that have very long time slices. And at this point, if all these queues are empty and you only have processes down here, those are your jobs that are running overnight, for example. Okay, so maybe you've got these jobs that are doing really heavy duty CPU calculations. There's no IO operations. Nobody needs to do an IO operation right away. And these guys can now they can get long runs on the CPU, and you're not wasting time context switching, context switching, context switching, context switching. Okay, all right. So this is considered a really efficient algorithm because it actually does round robin when it needs to. And it does long time slices when it needs to. I mean, an optimal algorithm would actually, down here, just let this process run to completion, then let this process run to completion, then let this process run to completion. But it has no way of knowing what that really means. Like, what if this process ends up in an infinite loop? Yeah. So what it settles on is very long time slices for processes that are down here in this low priority queue. They're considered to be long running jobs, so they get very long time slices. Okay. So now we have the blending. Essentially, we've got a blending of all three of these things. Okay. Oh, let me save this before I lose it. Okay. You're round robining on essentially that queue there, especially. Okay. And now, in a way, it isn't really round robin here, because when you take this guy and you put him up here, he returns always to some other queue. So essentially, it's not quite round robin here because you never go to the end of that queue. It is round robin literally on this one. You go over here. If you end up your time slice, you go to the end of the queue. and then you go back up to the front, you run here. If you finish up your time slice, you go to the end of the queue. So it's really round robin on this one. And it's round robin on this one. If you go here and you unblock, I'm sorry, if you go here and you block, when you unblock, you go to the end of this queue. Then you move up to the front. If you go here and you block, then you go back to the end of this queue. So in a sense, it really is round robin on this one, and it's really round robin on this one. The intermediate ones are not quite round robin because when you leave here, you always come back in the end of the next queue down. And if you get up to the front here and you run and you use up your time slice, you go to the end of the next queue down. So you can make the case that these are not quite, yeah, that's not quite round robin. You know, maybe you can kind of make the case that this one's not quite round robin, this one's not quite round robin, and this one's not quite round robin. So it's a modified, you know, because you go from this queue to that queue, from this queue to that queue. This one's round robin and this one's round robin. Okay. Then we have priority involved because if somebody unblocks, they get up here, now they have the higher priority over, no matter what queue you were working on. If somebody unblocks and ends up here, the next you immediately run, they would immediately move to the CPU. Okay, so this would be a higher priority queue than any of these. So when somebody unblocks and comes up here, they immediately go to the running queue, and whoever was running gets put down back here in their queue. And that's actually, that is one way you can end up back in this. You know, if suppose P9 was over here running, and then somebody unblocked and bumped P9 from the CPU, he would go back to the end of this queue. Since he didn't get time, he didn't get to finish up his time slice. You would say that if he didn't finish up his time slice, then he would go to the end of this queue here. So he would just go back here, let this guy jump ahead. Then when this guy blocked, then the next one from here would go over here. Okay. All right. So now, so we've got priority because we have these multiple queues. We've got round robin. And we also have shortest time to completion first because these guys are considered the short jobs. And the short jobs have highest priority. So someone who's up here is considered a short time to completion. It's going to be, they're assumed they'll make another IO request very quickly. If you put one of these over here and he doesn't make an IO request very quickly, then he's moved down to a lower level. Okay, so he stops becoming a short job. If you don't make an IO request and get blocked, you actually then would move to a lower level. And then maybe that's because maybe your IOs are all done at that point. So you made your last IO request, then now you get running and there's no more IO to do. So now you go back to here. Then when you finally get to run again, there's no more IO requests. So you end up moving down here. So you become a CPU bound process until you sometime later when you maybe need to make another IO request. Any given process in the real world of computing, and like if you look at processes running in big server farms, any given process tends to drift between a phase of being CPU bound and then a phase of being IO bound. So a process will need data. When it needs data, it'll need to make lots of IO requests to get all its data. So a process will be doing, it'll ask for some data, block, then it'll ask for some more data, block, ask for some more data, block, ask for some more data, block. Then when it's got all the data it needs, then it's going to start computing on that data. So then it'll finish out a time slice and it'll move to here. Then when it gets the CPU again, it'll finish out a time slice because it's still computing on the data it was given. So it read in a bunch of data and now it's going to compute. So it might take quite a while for it to process the data. At some point it gets down here and it does a lot of processing and it's finished processing the data, gets back over here and starts needing more data. Well, it needs more data, it makes an IO request. Well, makes an IO request, it goes up here because now it's going to probably go to an IO bound phase where it's going to get a bunch more data. And real world processes drift between needing a bunch of data, so they're doing lots of I/O operations. Then they drift into a compute-bound phase. They kind of move down these queues until they get down here where they're really computing. While they're really computing, any other processes that's doing their I/O phase will have higher priority. So you always let the processes that need I/O get their I/O quickly. So you don't have, like the picture we had to begin with, you don't want this, where an I/O bound process is waiting. Like he could have done an I/O request, say, he could have done an I/O request here. I'm sorry. He makes an I/O request. He could have made an I/O request here, but he has to wait till here to make it. Then he could have made an I/O request here, but he has to wait. He could have made an I/O request here, but he has to wait till here. See, he makes an I/O request, and he has to wait all the way to here to make another I/O request. Then he has to wait all the way till here to make another I/O request. That's the bad thing you want to avoid. When a process has started being I/O bound, it should get high priority right away. Okay. So if a process makes one I/O operation, assume he's going to make a lot more. Put him up here. Now he can keep making quick I/O operations. The I/O bound processes have very high priority. When he gets to being a compute bound process like these, then he switches to this long running time slices. So you're not wasting time on context switch, context switch, context switch, context switch. So when you get to being a real long running process, you want to move to this queue with really long time slices. Okay, we run out of time. Let me show you one last thing. If you go to this folder on multi-level feedback queue, there's a couple pictures that come from some other, okay, like look at this picture here. This is the queues from an older operating system called the Solaris operating system. Okay, he's got them reward. What this high priority queue was was this I/O bound one, and this is the CPU bound one. So this picture's upside down from this one here. Now notice I just made the time slices go from 30 to 150 milliseconds. Look how theirs go. This was a real operating system. This was a very famous version of the Unix operating system in the 90s. It used a 20 millisecond time quantum for the I/O bound processes, and it used a 200 millisecond time quantum for the most CPU bound processes. And you can see how the time quantums drifted: 20, 40, 40, 40, 40, 80, 80, 120, 120, 160, 160, 200, 200. Yeah, and they had a whole bunch of, see, they actually had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They had 13 of these queues. Okay. And the time quantums were, really varied from a very brief 20 millisecond time quantum, which were the very CPU I/O bound processes. They were given 20 milliseconds to do another I/O operation. And then once you got the things that were really long running processes, they were given a fifth of a second. See, this was 200 milliseconds. They had very long time quantums. Okay. Okay. So this was another example of this was oh no, let's see. For Windows, yeah, I don't know these numbers for, like, this was for Solaris. I'm sorry. These numbers for Windows, I'm not sure if I know where to find them. Like Windows does this algorithm. I'm not sure what time slice it uses for the I/O versus what time slice it uses. When somebody drifts from here down to here, how do the time slices get longer in Windows? What time slice do you give the I/O bound process versus the CPU bound ones? I'm not sure if that's documented or not. It probably changes all the time from one version of Windows to another. Okay, Windows actually has a huge number of these. Where's the picture? Oh, I'm sorry, this one. Windows has got 30 of these levels. It's got 30 of these queues, but it does a weird grouping of them. Yeah, there's 30 of these queues, but you don't drift all the way down. You stay in a band of queues. So for example, if you have what are called, if you're high priority, you would move from this queue to this queue to this queue to this queue to this queue, then you jump back up. If you did an IO operation, you'd back up to here. Then you drift down to here. Whereas these, if you're above normal, you drift down to here. Then if you did an IO operation, you go back up to here, not up to here. Okay, so you stay within these bands. Not really sure what the motivation for that is, but even though there's 30 different queues, any given process only moves between 5 of them. So it would move between these 5 levels. If you go to Win Task Manager, see this column here are these names: high, above normal, normal, high, above normal, normal. So this is a process that's moving between these queues. This is a process that's moving between these queues. And there's some overlap. So in this queue here are some high processes and some above normal. See, there's overlap. This queue actually holds some of these processes and some of these processes. Now, this process would only move between these queues. A process over here would move between these queues, but they could share that queue. It's really kind of complicated. Yeah. So any given queue is shared between two priority levels. An above normal process moves between these queues. A normal process moves between these queues, but this queue can have both above normal and normal processes in it. That's how you read this. So the queues are really, it's a pretty complicated version of this. You know, it's essentially this picture here where you move between these queues here, but these pictures are overlapping. Yeah, and high priority processes have their set of queues. Above normal processes have a different set of queues, except that they're shared. Okay, so this is the idea. They're using this picture with an extra layer of complexity. And I don't know what the time quantums are for each one of these levels. Like, what is the amount of time you get if you're at this level versus amount of time oh, and Windows doesn't use any of these. The real-time queues, none of them are being used. The current version of Windows doesn't actually use any of these queues up here. It actually only has 15 queues. It uses from here to here. The operating system was designed to have 32 queues, and then they never sold any real-time version of Windows, so they're never using these queues up here. They're not in use. So it's, this is how you end up with a really super complicated operating system. You design features into it that you never end up using. So the operating system has all this stuff and then doesn't use half of it. Okay. So we'll talk more about this on Wednesday. We'll finish. There's a few more details to this to talk about, but this is the structure. This is the main idea of the multi-level feedback queue operating system. It's again, it's optimizing this problem of how to solve this picture. It's really trying to solve this problem here. How to get P0 to be cutting in line. How do you get the IO bound process to cut in line? Okay, that's the whole crux of the matter, and it takes this setup to do it. Okay, so we'll quit there, and we'll finish this up on Wednesday, and then we can start talking about virtual memory. Okay, and anybody got any last second question? Any last second question about this? Okay, so we'll stop sharing, and we'll meet again on Wednesday, and we'll finish multi-level feedback queue on Wednesday, and then maybe on Wednesday we'll start virtual memory. Okay, see you on Wednesday.